After revising the isomerism and stereochemistry, we need to talk about organic reaction mechanisms. And in general, the conversion of a reactant into products involves always breaking and forming of covalent bonds. And always when covalent bonds break and form, the pairs of electrons in the bond move to different atoms, what we show then by drawing an arrow. And there are three different reactive intermediates. The first one is the carbocation, the second one is the carboanion, and the third one, the radicals. And then we need to think about the charge. So in general, there are two different ways how we can split a sigma bond. And these two different ways are indicated here. So for the homolysis, we can draw always two arrows, which indicates that we have a splitting of this two electron bond, and one electron moves to the one direction and the other to the other. So at the end, we have two radicals, and a radical has always an unpaired electron. The second type of splitting bond is the so-called heterolysis, and here we only draw one arrow, and that means that we end up with ions. So in other words, one of the binding partners gets all electron density, and we form a cation with positive charge and an anion with a negative charge. If we now have sp3 hybridized carbon with a tetrahedral binding angle, and we do homolysis, so then we get a carbon radical where the unpaired electron is in the leftover p orbital, and the carbon atom is now sp2 hybridized, and we also get a bromine radical. This you can see here. So we draw two arrows as we do a homolysis, and then we end up with this planar carbon radical and the bromine radical. Of course, we can also do a heterolysis, and then we draw only this one arrow. That means that the carbon-bromine sigma bond will be split in that way that the bromine anion gets the complete electron pair, and we end up with this bromine anion here, and then with a planar carbocation, and this carbon atom is then sp2 hybridized. And there is no electron left in the p orbital, which is energetically favored. Then we have a third thing what could happen, and this is that the carbon takes the negative charge. What happens, for example, if the carbon atom gets deprotonated? And then you can see it here. So we have at the beginning the sp3 carbon atom, then a negatively charged base is approaching, and the carbon atom will be deprotonated. And then we end up with either sp3 hybridized carbanion, which is pyramidal, or an sp2 hybridized carbanion, which is planar. And this depends on the substituents. So if we have an R group which can stabilize the negative charge by resonance, then the carbanion is planar. Otherwise, it will be pyramidal. And now we want to go one step further, and we want to understand if we have a certain intermediate, how can this be stabilized? And we start with the carbanion. And here it is important that you know how the groups, the substituents, react. So that means, do we have an electron withdrawing group, or do we have an electron donating group? And depending on the characteristics of the R groups, we can then estimate how the reaction will proceed and which intermediates are stabilized. And we can have, for example, the so-called inductive effects, the I effects. And if we have a plus I effect, which is shown here, then we know that the R group is an electron donating group. That means the groups will push the electron density towards the carbon, and in this case we then have the electron density going from 3 R groups towards the positive charged carbon. That means we have a very stable tertiary carbocation. And if we go to, say, less R groups with plus I effects, then the stabilization will get minor. And if we end up with a material carbocation, then know that the hydrogen has no plus I effect. So this carbocation is not very good stabilized and is then the least stable version. And besides the inductive effects, we can also have hyperconjugation. And hyperconjugation means that the orbitals of the neighboring carbons can in some way overlap. And this again leads to a stabilization. So what is important to know here is that we have let's say a donation of electrons from sigma C carbon hydrogen bond, or also from a sigma carbon carbon bond, which are next to the carbocation and the unhybridized p orbital. This is important. Otherwise, we cannot talk about hyperconjugation. But if we have this, then we can say that the empty p orbital here of the carbocation and the sigma bond of the neighboring group, let's say the alkyl group here, can then align so that they can that the empty p orbital can be stabilized as from this neighboring alkyl group. And this is the so-called hyperconjugation. Besides the hyperconjugation, we can think about the mesomeric effects as well. And as already seen here for the plus I effects, also the plus M effects can stabilize the carbocations. And mesomeric effects means that the delocalization of electron density through a pi bond is somehow involved. So if we have a plus M effect, that means that we have either a pi bond or, for example, the lone pair of the oxygen. Then this lone pair can switch in position, and hereby we can stabilize the carbocation as it is indicated here. So we have here the positive charge next to the carbon. Then here the neighbor atom is an oxygen with 2 lone pairs, and then the lone pair can flip here so that we build a new pi bond, and the positive charge will move towards the oxygen. And hereby we stabilize the carbocation, and this is then another way how we know that the carbocation is stabilized. And if we then compare the stabilization for the carbocations with the carbanions, then we can see that the trend is exactly the opposite. Here, if we compare first of all the tertiary carbocation, we know that this can be stabilized by 3 plus I groups. And if we then compare it with the tertiary carbanion, we see that this version is the least stable. We can think about it. Now we no longer have a positive charge, but now we have a negative charge. That means if we have 3 substituents which want to push the electron density towards the carbon, but the carbon is already negative, and this will not lead to stabilization, but let's say to instabilization then. So the carbon does not want to get additional negative charge anymore. So then we know automatically that the most stable carbocation will be the version where we do not have plus I effect. So, for example, this carbanion with only hydrogen as substituents. And yeah, to summarize, we always have to remember that carbanions can be stabilized by -I groups, and carbocations can be stabilized by +I groups or by +M effects, and also by hyperconjugation. So now, after the very general explanations for the possible intermediates, we now talk about some organic reaction mechanism where the nucleophile and the electrophile interacts with each other. And this kind of reaction is called polar reaction. And first of all, a very simple case is that we have a negative charged nucleophile, which is the electron donator, and then we have a positive charged electrophile, the electron acceptor. That means we start with more or less the attack of the negative charge to the electrophile, and hereby we form a sigma bond. And here it is important to remember that the overall charge of the system should be maintained. So if we start with two charged ions, so with a positive and a negative charge, that means the overall charge at the beginning of the reaction is 0, and then we have to end with an uncharged new product. It cannot happen that we start with an uncharged starting point, and then we end up with a charged one. And also important is that we think about the possibilities of a nucleophile. So first of all, the nucleophile can be negatively charged, but it is not necessarily needed that there is a negative charge. It can also be that the nucleophile is neutral. Then we just have a lone pair on the nucleophile, which can also then, let's say, move to the positive charged electrophile. And if this is the case, then we start just with a positive charged electrophile, and then we will end up with a positive charged new product. So this is again the principle of maintaining the overall charge in the system. And also important is that always, if we want to show that the electron pair moves, we always draw this arrow, and this arrow starts always at a negative point and going to the positive. So really the way like the electron pair will move. And if we talk about polar reactions, we know that polar reactions are more or less the most common reactions in organic chemistry. And polar reactions can take place either between two polar molecules or between one polar molecule and one charged molecule. And in principle, we have three main types of polar reaction. First of all, we can have an addition. Then we can have an elimination or a substitution reaction. And an addition reaction means that two reactants react to form one product. And if we talk about addition reactions, then we can subdivide this class of reactions into either electrophilic addition or nucleophilic addition. And the molecules which perform such kind of reactions very often are unsaturated compounds. So we then talk about alkanes and alkenes, or also about aldehydes or ketones. So very easily said, we need a double bond or a triple bond in the system. And then if we have such a double or triple bond, we know that this part of the molecule will act as nucleophile. And yeah, here we can see the example for the electrophilic addition reaction. So we start with the alkene. Here, the pi bond will act as nucleophile and move the electron pair of this double bond to the positively charged electrophile in the first step, the addition step. Then we create a carbocation as intermediate, and then in the second step, another nucleophile will go to this positive charged carbon, and then we end up with a newly formed alkane. So in principle, we can remember that electrophilic addition reactions can produce alkanes out of alkenes. And here is the example for the nucleophilic addition reaction. So here we start with a negatively charged nucleophile, and we have as electrophile the aldehyde. Then we have a nucleophilic attack, the partially positive charged carbon, because the oxygen has a higher electronegativity. That means the electron density will go more likely a bit to the oxygen instead of the carbon, and hereby we have a partial positive charge at the carbon. So then we have the first addition step. That means the nucleophile will now bond already to the carbon, and the oxygen will then end up with a negative charge. So we have an alkoxide ion as intermediate. Then in the second step, we need to compensate the charge, what we do with a protonation step, and then we end up with this alcohol. And the elimination reaction can be seen as exactly the opposite of an addition reaction. So that means we have saturated compounds, which we convert then into unsaturated compounds. And here you can see, for example, the reaction between a negatively charged base and an halogenoalkane. Then in the elimination step, we will deprotonate the alkane because the base will attack the hydrogen here, and then we will let the electron pair go down, forming a new carbon-carbon double bond, and the leaving group here, the halogen, will go out of the molecule, and we end up with this newly formed alkene. And here, if you directly compare the addition reaction with the elimination reaction, you can see that the addition reaction is a two-step reaction mechanism, whereas the elimination reaction is a concerted one-step reaction mechanism.